Okay, hello everyone. Again, for our session norms, please engage actively and be open and ask away. There are no dumb questions, and we also want you to understand everything. So if you have some things that are unclear yet, don't be shy to ask away, and of course, be respectful for everyone. Again, for this session, we will be using the live questions tab or channel or of our Discord server. So if you're not there yet, you can join it. It's sent on your welcome emails. And yeah, just so that if you have some unanswered questions, we can answer them asynchronously on Discord. Also, the homework for lecture one still open, and yeah, you can still submit on it. And yeah, and some of you have mentioned that you filled the form up but it didn't mark as done automatically, so don't worry about that. We will be getting your responses from the forms or Google Forms directly, and not from Google Classroom. Also, the homework for lectures 2 and 3 will have extended deadlines since some of the concepts are new to you. And yeah, we will send them right after this session for tonight. And yeah, so please look out on Google Classroom. Also, as you answer the homeworks, you can use our Discord server. You can get some help. You can ask us, tag us. All right. And if you need some help, we have the homework help channel. If you need a place to study together, share screen, we have study rooms for you as well. Okay, so for today, we will have lecture three, algorithms and complexities. So the first session would be more about basic programming introduction on Python. So that it's the series is called quantum computing. So yeah, there's gonna be programming here, and yeah, we'll have a session on how you can get started with IBM quantum experience, and a talk, a keynote on the complexity of algorithms and its implications in classical and quantum computing. So, before anything else, we would like to welcome Sir Roland Otodoy, Professor of Physics in University of San Carlos. He has been very helpful in organizing this event. So, yeah, let's give him a virtual round of applause. Hello po. Good afternoon.
Our students from different universities, faculty members, ladies and gentlemen, good afternoon. Much has been said about quantum computing's impact in science, engineering, and industry, and consequently on the economy. In a broader context, I rather use the term quantum technology or quantum phenomena to emphasize the broader impact of quantum physics, almost all facets of science, engineering, and industry. This term includes quantum communication, cryptography, quantum sensing, and quantum metrology. Eventually, the term quantum technology evolves into a field popularly known as quantum information science. DOST has a roadmap on quantum technology stipulating by 2030 we will be able to build a quantum-enabled economy. This requires an army of quantum proficient manpower. This event, organized by One Quantum and its partners, is one of the steps that will equip our manpower for the basics of quantum algorithms and programming. It is in this note that I welcome you all to this lecture on quantum information science. Thank you for your participation.
Awesome. Thank you po for that, Sir Roland. All right. Okay, at this juncture, um, yeah, I know that we're very excited, and Sir Roland mentioned a lot of the applications of quantum computing and quantum technologies in general. But before that, let's step back a bit again and yeah, have a beginner or like an introductory session on programming as it is a one of the building blocks in terms of skills that we will use and would be helpful on this field. So yeah, I'm happy to introduce to everyone Sir Bobby Corpus, the president of One Quantum PH and a board member of the OST Shared Quantum Technology Board, as our speaker for this session. Hello po, Sir Bob.
Hi. So thank you very much, Jabez. Yeah, so um, this is actually one of the building blocks of our lecture series. We will be doing a lot of programming, and we just want to make sure that everyone is in the same page. So I know that most of you already know Python programming, and um, some don't have knowledge yet. So we'll just make sure that we'll cover all of our bases. Okay, so I will try to cover this in 30 minutes. So I will now share my screen. Okay, share. Okay, so introduction. Yeah, so Python is actually not a difficult language. In fact, if you're already a professional programmer, Python is so easy to pick up. Like, for example, in an hour, you should be able to pick it up. In a day, you can probably do some serious programming. Yeah, so, and also Python is one of the, I have a friend, mathematician friend, who said that Python is like, it's like mathematics. It's a mathematician's tool because the syntax is really very, very simple and very nice. Okay, so let's begin. Okay, so Python. So Python is created by this guy whose name is Guido van Rossum. So he's currently, last I checked, he's with Google. So Python has been around for some time. So I remember way back in the 1990s that that was the first time I was able to hear about Python, and I recommended it to my friend, but I didn't really know. I didn't really use it, but he was very happy. So it's high level language, and it's interpreted, so which means that it's not compiled, um, but it also calls. So which means it's not as fast as some languages like C, but it calls languages that are written in C, and that's the reason why it can be fast as well. It's the dynamically typed, so the interpreter will just so in languages there is there's a type like your variables. It can be a text like or a string as they call it. It can be a number. It can be a boolean. We are going to talk about that later. So in other languages, Python, in other languages, you have to declare that this variable is a string. In Python, it will just be inferred. So, and it's open source as well. Okay. So in any programming language, we always begin with um, variables, and when you name variables, there are some things that there are some rules. Okay, in naming variables. So variables usually include letters, numbers, and underscores. Okay, you can create a variable that starts with a letter or underscore, but not with a number, and it is case sensitive. So which means if you have a variable with different cases, like this one here, they are different. And of course, do not create variables with names like if, else, class, because those are reserved words in Python. And when you initialize your variable, you assign it a value. So you use the equal sign. Okay, so example, my age equals 15, student name equals Alice. Okay, now in Python there are, as in other programming languages, we have data types. So among those data types are numbers, strings, booleans, so and many others, but we are going to talk about them. So numbers, this can either be an integer, okay, or what we usually know as those numbers that don't have a decimal point, or these are whole numbers, and it can be positive, negative, 0, and floating point numbers. These are numbers that have a decimal point. And using in numbers, so there are operations that you can do with numbers, and these are the usual addition, subtraction, multiplication, and this one is modulus is very very important when we are talking about security, because most of our security are using modular arithmetic. So that's what's make them very hard to crack. Okay, so string. These are your usual text, like for example, your name. Okay, hello Python. Yeah, so when you create a string, you enclose it in single parentheses or double quotes or triple quotes for multi-line strings. And then you can do concatenation. You can concatenate the string using a plus sign. The repetition, you can slice it, you can index. So slicing means that you can you can create you can get a substring out of your string, and these are some things that you can do, like methods. Make it uppercase, make it lowercase. Replace a certain part of the string, or if you have a comma delimited string, you can split it, okay, into an array, and then get the part of the string that you like. Okay, so if you have any questions, don't hesitate to ask. Okay, Boolean. Okay, these are true or false. So Booleans are used in conditional statements, okay, or conditional statements like if then else, or when you want to terminate a loop, you use this Booleans. And they also have Pythons also have lists like this one here. Okay, apple, cherry, banana, and given a list, you can also append to that list. You can access an element, okay, or remove elements. Okay, so, yeah, I forgot to find myself. And tuples. So these are similar to list but are immutable. And these are enclosed in parentheses. Now, so for example, coordinates. These are tuples. Dictionaries. No? So these are this is a, well, we call it a data structure that allows you to define a key and a value. So like this, key value pairs. And so dictionaries are very important if you want to be able to access your data very quickly. Okay, so you only need to know the address or the key, and then you get the value. Normally, if you have a list and you want to access and you want to find a value of that list, usually you need to iterate to find that value. And then sets. So these are the same as mathematical object that are what we call a set, and the elements of the set are unique. Okay, so as the same as the definition of a set in mathematics. And then so usually when you program, sometimes you have a certain string and you want to and it's a, like, for example, a string, but it's actually a number. So in order for you to be able to do some arithmetic on that, you have to convert it first into a number before you can do that. So these are some of the functions that you can do in order to convert that string into a number. Or, for example, if you have a number, you want to be able to print it, to concatenate it into a string, then you just use the str method. Okay, so as I like to say to all of the people who are, asking for advice, how do I I want to learn programming, what are the things I need to know? So variable is one of them. Second is the control structure, if then else. Okay, third is the and then the while loop. And then third is creating functions. And once you're able to do that, the next thing is probably reading and writing files, no? And the good thing about reading and writing files, that is also the same as reading and writing into a internet connection. So it's very abstracted. So once you learn that, it's very easy to program. So control structures, these are the conditionals, no? So like if then else. Yeah, so the way you write in Python, so Python doesn't have any like, it doesn't terminate in a semicolon, unlike in other languages which need a semicolon. And it's also very strict with spacing. So the space is part of the Python's language. So if you commit a mistake in the spacing, then your program will not run. It will have an error. So this one here is how you line number 2 is how you declare your variable. No? So it's so a variable x is given a value 10. So which means this variable is a integer. And then here you do this is your conditional. So x greater than 5 will evaluate into a boolean. No? It's either true or false. And if it's true, then it will execute the next line. Okay, x is greater than 5. Okay. So, and if you have other conditions to check, then you can use the elif keyword. And then finally is the else clause. Okay. So I think this is very self-explanatory. So so as you can see, Python is really readable, right? So it's even it's the best language to teach your kids. Say yeah, the moment they know how to type. Okay, so this one here is an example of a list. Okay, and then so you declare a list of what you call this, fruits, and then here you can then do a for loop. Okay, so for fruit in fruits, print fruit. Okay, so very simple. And then you can also do a range, no? Like for example, you want to you want to print, in this example, you want to print all values, okay, between 0 and what do you think? 2, okay, 0, 1, 2, 0, 1, 2. So 3 is not part of the range. So you will print I. Okay. So let's So before we do that, so let's let me just show you the okay. So this is one of the things that I want you to do later. Probably we can already send this Javas. Okay. So the while loop is another way to loop over your over a you know so another way to loop. There are many ways to loop, and you can loop over a counter. You can loop over a collection of items in the list. No? So for example, here you loop over a counter, and then you decrement the counter until the counter is less than 3. Oh, sorry, until the counter is greater than 3. Sorry, great. Yeah, it's while the counter is less than 3, so which means it will work from 0 to 2. Once it hits 3, it will then terminate. Okay. And also in Python, you can do exception handling. Huh? So in order to create a robust program, you need to be able to handle errors, anticipate errors. So when you're already programming a very serious application, and you don't want your application to be flaky, and so you want it to be robust, so you have to do some exception handling. And the keyword for that is try, and do your operation. And then if there's an exception, like for example here, the exception is 0 division error. So you will be able to print division by 0 is not allowed. No? But if you don't do exception handling, then it will just fail and your program will terminate. Okay. And you can also do some there's another keyword called finally. So this keyword will be will be uh, will be executed, okay, regardless of whether the result is okay or not. Okay, so if there's an exception, it will be executed. If there's no exception, it will still be executed. So finally is used in order for you to clean up things. Now, like for example, you are reading a file. When you read a file, you when you read a file, and then you process something in the file, and suddenly there's an exception. So what will happen is that if you don't clean up, then you will have a lot of resources that are not freed up in the operating system. So finally is a way for you to be able to tell the program, okay, whether there's an error or no error, since we open a file, then we have to close it. Okay, so that's where you put the final. And then creating functions in Python is also simple, very simple syntax here. So you just the keyword is def, and then the name of the function, and then the parameters. Okay. So after that, you put a colon and an operation that you want. So and then to call a function, you just call it by its name. No? So for example, here we define a function called greet with a parameter name, and then you can just do it like this. Okay, so greet as. So functions can be void, which means that it doesn't it's a fire and forget. It doesn't give you a return value, or it can return something. So usually we expect some in our mathematics, when we define function, is something that returns something. It's It's something that returns something. Okay? So in here, we define add, and then the parameters, and then we return the sum of A and B. Okay. And then still the same. Okay. So since this function is returns a value, then it would be, it would be good if you can capture that value case, or and then use that value in the next step. So in here, you add 5 and 3, and then you print the result. Okay, so that's it. So the next thing we'll do is okay. The next thing we'll do is we have to do this now. So let's do some exploration. Okay. I'll put this in the chat.
Oh,
Okay.
I sent it.
Oh, you said it. Okay. Okay, so guys, no. Okay, let's do this very simple thing now. So in here, the first thing is we're going to create a variable and then assign it integer. Assign it so we create an integer variable and assign it called age and assign it a number. No? So example, name is age. Okay, was 5. Okay, and then assign a float. No, so average score. Sorry. Okay, average score equals, for example, 11.5. Okay, it's a float. And then a string, no? For example, favorite color. Color equals, okay, blue. Okay. And then we are going to print each variable and use the type function. So for example, print the variable age, okay, and then type age, okay. So we can. So by the way, guys, no, I did not probably introduce to you this. This one is called a Jupyter notebook, and it's so it's a Google Colab. It's one of those nice things from Google that you can use for free. For our and Jupyter is a really very nice interface for programming in Python online using the browser. So this will be like the user interface that we'll be using for the rest of the lecture series. And the IBM Quantum Experience also has this user interface. It's based on Jupyter, but different, but different. Well, this different look and feel. Okay, so that's how you do it. Okay, print average score. Okay, and type average score. Okay, it's good that it also has completion. Huh? So it will complete your. Okay, so here it says that 5 is an integer, 11.5 is a float. Huh? And yeah, you can also do that for your favorite color. Okay, so in here, so Javas, you can interrupt me if there's any question. Okay? And actually, I don't know how we can do this now. So I hope that the participants, especially those who are new to Python programming, if you can also do what I'm doing. Okay. So string manipulation, you create a string, okay, with a value of Python is fun. Okay. So guys, now in order to save time, I'll just paste this one. Okay. So Python is fun, and then in here you have a string. You can get the length of the string, and then and in here, so you can uh, look at the string as an array of characters, and this is where you slice those. This is one way of slicing the string. Okay. So here, so when you say by string colon 3, okay, it means that it will begin at 0 and then end at 3. Okay, and here begin at 0 and end at 6. Now I can, of course, begin at 3 and end at 6. What will happen? Okay, so it becomes, it begins at 3. So by the way, it is the index is 0 based. Okay, so this is 0, 1, 2. So that's why when you say, can you slice my string so that you print only characters from index 6, sorry, from index 3 to 6, then so 0, 1, 2 is so P is let me make that bigger. Okay. Okay, so P here is index 0, and then Y is index 1, and then T is index 2. So letter H is index 3. Okay, so 3, 4, 5. Okay, so 3 to 6, it means that uh, starting at 3 up to 5. Okay, it doesn't include the this last number here, 6. Okay, so basic arithmetic. Okay, create two integers, integer variables, perform addition, subtraction, multiplication, division. Okay, and then perform exponentiation, find the remainder, modulus. Okay, let's do that. Okay, here, just make sure that I copy it properly. So we have two numbers, number 1, number 2, number 1 and 2. And then set them to these values 10 and 5, and then do the addition, subtraction, all of this. This is the exponentiation, and this is the modulus. Okay, so modulus is nothing but the remainder, right? The remainder when you divide. So, for example, what's the if you divide 10 by, sorry, what's this? If you divide 10 by 3, what would be the remainder? Okay. Okay, it's 1, no? Because 3 times 3 is 9, and the remainder is 1. Now, so create a list of 5 different fruits, print the second and the last fruit of the list. Okay, so let's do that. Just copy this one here. Yeah, so this one is creating a list of fruits, and then you print the first. Okay, sorry, index 1, which is banana, and then and also you can index it from the last item. So for example, -1 here is the last item, kiwi. Okay. So it's shortcut. Now add a new fruit to the list, change the third fruit in the list, and remove 1 fruit, okay, from the list. Okay, so to add 1 fruit, you just append. Okay. Okay, so fruits that append mango, and then print what happened, and then change cherry to strawberry. Okay, and then remove banana. Okay, so let's do that. So here we added mango. Okay, and then we change fruit number index number 2. Okay, it's actually the third fruit from strawberry. You know, so cherry now becomes strawberry, and then remove banana. Okay, so when we remove banana, what happened is it disappeared, no? And it's the new list. Okay, so create a new list of numbers and print the sum average. Okay, sum and average. Okay, so this is how you do it. Okay. So you have a list of numbers, and this one is a built-in function. So you sum the numbers, and then you get the average. Okay, sum is the total, and the average is you get the length of your list. Okay, so these are things which I did not mention earlier, but you'll be able to discover this as you go along. We just want to cover as much ground as we can. Okay, so that's it. And do I still have more time, Javis?
Yes, for sure. Sure. Go
Okay,
ahead.
so here we create a tuple, and then we try to change one of the colors. So we create a tuple for colors. Okay, so we can print that. Colors. Okay, so let's try to set the first one to yellow, and then it will tell you that you cannot do that, no, because tuples are immutable. Okay, now we create a set of 5 different numbers, add a new number to set, and remove one. Okay, and then check if a specific number is present. Okay, so this is an example. Okay, so you have a number 0, 1, 2, 3. Sorry, 1 up to 5, and then you add 6, remove 2, and then check if 4 is in the set. Okay. So let's do that. So let's print number set. Okay, number set. Okay, and then I'll just copy this. Okay, what happens if you add 6? What happens if you remove 2? Okay, so let's do that. If you add 6, this will be the result. You remove 2, this will be the result. So it's really nice to be programming because it's a creative process, and you can see immediately the result of your effort. Okay. Creating accessing dictionaries. So a dictionary is a key value pair. So here, create a dictionary representing a student with keys like name, age, and grade, and then access and print the student's name and age. Okay. Okay, so here we have a variable called student, and this is how you create a dictionary. You know, so this is the key and the value. Okay. So key and value, key and value. And in order to get the okay, so print the student name. Okay, so this one represents a student, okay, whose name is Alice and whose age is 16. Okay, so let's do that. Okay, so name is Alice, age is 16. Okay. Yeah, so this is a very dictionaries are very nice data structures in Python. Okay, So later in complexity, in the session of Elmer, he will be talking about complexity of algorithms. Um, so the complexity of algorithm, he will probably tell you what the complexity of dictionary is. So I will leave it up to him to tell you what that is. Okay. Modifying dictionaries. So you can also create a new key value, and then you can change the value of a student's grade, okay, remove the age from the dictionary. Okay, so let's do that. Okay. Okay, so here you added a new key, and then set it to a new value. So favorite subject, math. And then since the grade is already defined here, you can also change that, okay, by just referencing it. And to delete the age key value pair, just use the del keyword. Okay. Okay. Okay, so let's print it. Okay. Do that. I'm going to print student. Okay. Oops. Happened. Key error age. Oh, key error age. It's because I already deleted it. Okay. Okay, so the good thing also about programming is the more mistakes you create, before you deploy your application, the better. Okay. Mistakes make you learn. Okay, so don't be afraid of seeing those things like this, no? When you become very good at programming, then this one is actually very helpful to you. So the ability to read errors like this, and be able to, and also the ability to resolve using this log error messages is very important when you want to be a programmer. Okay, data type conversion. Okay, so here convert a string into a number. Convert a string containing a number into an integer float, and then convert a string into convert integer into a string, and concatenate it into another string. Okay, so here we have a string called whose value is 42. Okay, it's obviously a number, and but it's a string, so which means that we cannot do arithmetic. Okay, so if you want to do some arithmetic on it, you have to convert it into a into an int. Okay. Okay, so for example, 42 here. What would happen if you do this? Huh? Print num str plus 1. Okay. Okay, so you cannot do that because the Python interpreted it as you want to concatenate the number 1 into the string 42, which is not possible. Okay, so okay, so that's actually my cue. I'm just gonna finish this. So in order for this to be successful, it depends on what you want. Okay, so for example, if you want to do 421, then you convert this into a string, no? So str, sorry, this one here, str. Okay, and that will give you so it was not closed, and that will give you 421, right? That's a string concatenation. But if you want to do arithmetic, then 42 plus 1 is 43, right? So you have to convert this into an int. Okay, and remove this one here. Okay. That should give you 43. Okay. Now, there are actually many more that we can do, but I leave this. Okay, I leave this to you as an exercise. Okay, so of course, please use references also from the internet. There's a lot of Python tutorials in order for you to do this very simple exercises. Okay, so yeah, I think that's it, Javis, for me.
Thank you for that. Okay, all right. So yeah, we've been teasing you a lot on quantum yet, right? But yeah, these foundational topics like math and programming are really integral on how we can interface with real quantum computers. So yeah, how we want everyone to be on the same page about that. All right. So before moving forward, let's have a quick 10-minute break. Okay. Okay, at this point, yeah, we talk about a bit more on the algorithms and programming in general earlier, and now we'll be talking about the complexity of these algorithms. And yeah, let's look into the context by which we can see the difference between classical and quantum computing in terms of complexity and how fast these machines can solve certain problems. So, without further ado, I would like to introduce our talk for about algorithms and complexity, Sir Elmer Paramo, and a very active member in One Quantum Philippines and a DOST Senior Science Research Specialist at DOST ASTI. All right. Hello po, Sir Elmer.
Thank you, Jabez, and good evening, everyone. Good evening, Sir Barbie. Yeah, Jabez was I'll be talking about uh, complexity of algorithms. So this is just this is a continuation of Sir Barbie's lectures. Also, he discussed Python programming. So it's just up uh, that in order for us to make our code more efficient, it pays to have a better understanding of the complexity of the algorithms that we're implementing. Uh, for example, if we're using the Python programming. So let me just share my screen. So can you see my slides right now?
Yes po. Very clear.
Thank you, Jabez. So yeah, good evening. So today we'll be diving into the intriguing world of algorithmic complexity. So its importance, understanding, and the popular big O notation, uh, and some common examples. So here's the roadmap for today's talk. So I'll start by I'll start by understanding what algorithm complexity is and why it matters. And then we'll discuss the big O notation, which is a fundamental tool used for the purpose of for actually uh, to know how efficient our algorithms are, and it's also important to have a basic understanding of some functions uh, and or the growth of functions, and then I'll give you some common examples and types of algorithmic complexity and wrap it up with some Python examples. So let me just define what an algorithm is. So an algorithm is basically a finite, well-defined set of step-by-step instructions or procedures to solve a specific problem or perform a task. So an algorithm should have the following properties. So number one, unambiguity. So it means that each step in the algorithm should be precisely defined and clear. So it should not be equivocal. So it should be clear for each of the steps should be defined, and you know what you're actually what the computer is actually doing for each of the steps. Next, it should be finite. So meaning if you execute an algorithm, it stop at some point. And then effectiveness. So basically, it means that every step of the algorithm should be basic and executable. It can be carried out. And generality. So a good algorithm works for a broad category of problems, not just for a specific instance. For example, if your algorithm is to find the common greatest divisor of two numbers, it should work for all pairs of integers, not just for some pairs or for a specific pairs. And how do we represent algorithms? We actually represent algorithms. We can actually describe them using natural language. Okay, that you can tell your friend, oh, this is how my algorithm works. By enumerating the steps, for example, excuse me, or you can use flowcharts. So flowcharts are visual representation. You are going to use some shapes, so standard shapes, like for example, diamonds, squares, and so on. Then you connect them with arrows. So there's an advantage of using flowchart. But for example, for simple algorithm, that's good enough. That's good. But if your algorithm takes a lot of several steps, it's very tedious. But there are some tools that you can use to uh, to design your algorithms or using flowchart. Another example is by the use of pseudocode. So pseudocode is a go-between the natural language description and the actual programming language. So, for example, you want it to look like a certain programming language, but at the same time, it's still intuitive enough to be understood by non-technical users. So you can use pseudocode to describe how your algorithm works. And of course, algorithms usually are written in programming language, just like the Python programming language. Basically, if you know how to program in Python, okay, you can actually implement your algorithms using Python or Java or whatever programming language. So those are the different representations of an algorithm. So let me just give you some examples of algorithms in computer science. So in computer science, we usually discuss this for example, there are courses in computer science, like for example, analysis of algorithms, or even in discrete mathematics. Okay, these are talked about, but the most common topics that are being discussed in algorithms are this searching, for example, linear search, binary search, or DFS, and then breadth first search. And then this is the classic examples of algorithms that you would be talking about if you are enrolled in a computer science class, the sorting algorithms. You have the insertion sort, selection sort. So there are different ways of, for example, given an array of numbers. So you can use heuristics, for example, to sort them, but you have to identify step by step how the computer will perform the sorting. So there are different well-known algorithms for that. So you have the insertion, selection, shell sort, heap, merge, and quick sort. So all of these have different complexity, which I'm going to discuss later. What complexity means, or meaning the efficiency of running, the efficiency in terms of running time, the efficiency of how your algorithm executes. Okay, so let me just there are also other types of algorithm in classical computing, like for example, the string search. So that is also a very uh, useful algorithm. For example, if you want to search for a particular patterns in a long length of string, so you have the Boyer-Moore, the Rabin Carr, the KNP, or the Knuth Morrison-Pratt algorithms. So these are very useful algorithms that you'd like to take advantage of. Invented by famous computer scientists. And also, for example, we also deal with data structures like graphs and trees, and there are algorithms to actually process them. Like for example, I think Sir Bobby mentioned about different data structures in Python. You have the list, you have the dictionary, you have the tuples. For example, there's also you use data structures in computer science to make the representation of your data more efficient, so that algorithms will lend itself the data will lend itself well to the algorithms when you process them. So in graph processing, you have the Dijkstra for shortest path algorithm, Bellman-Ford, Floyd-Warshall, Kruskal, and Prims for the minimal spanning trees. Of course, my area is actually in AI, so I'm familiar with these machine learning algorithms. Like for unsupervised, you have the k-means clustering, hierarchical clustering, and for supervised, you have the random forest, SVM, LSTM, and the backpropagation and gradient descent algorithm used in artificial neural network, or the multi-layer perceptron. And you also have other algorithms in other fields, like for example, in information theory, you have the Huffman coding. In number theory, or for finding the greatest common divisor, you use the Euclid's algorithm. So these are some of the famous algorithms we use in classical computing. But later on in the series, in the lecture series, we will be exposed in more detail with quantum computing algorithms. Like, for example, the Shor's algorithms will be discussed in the weeks ahead, and the Grover's algorithm, and also the Deutsch-Jones and the Bernstein Vazirani algorithm. So these are names that you would probably encounter if you're in computer science, but these are basically the names of famous common algorithms we use in computing. And in fact, these are, I'd like to just share the books that we use in computer science. This one is a classic. We call this the one on the left, we call that the CLRS, or book, or it's by Corman, Larson, Rifes, and Stein. So that's a classic book in algorithms. You want to go deeper, but the books on the left are honorable mentions. And actually, in the book by CLRS, an algorithm is any well-defined computational procedure that takes some value or set of values as input. So that's a keyword there, input, and produce some value or set of values as output. So basically, we're somehow, Sir Bobby mentioned something about functions. So functions, you have input and you have output. So basically, in a way, you can look at it as implementing a certain function to accomplish a task. Okay, so an algorithm is thus a sequence of computational steps that transforms an input into the output. So, and at the score of algorithmic complexity, so basically, we want to measure the efficiency of an algorithm in terms of the amount of resources it uses, namely time and space. So there are two types of algorithmic complexity. You have the time complexity and the space complexity. So for the time complexity, we normally are after the efficiency or the running time of a particular program or a particular implementation of an algorithm, how long it takes. In terms of the input, the input here is basically your data, the size of your data. For example, if you input, let's say, an array with the size 10, and you run that you code that in Python and you run that program and you timed it. For example, you put in some time start and time stop after the execution, and then try adding more numbers to that array, and then you run that program again and see how the execution time changes. So basically, that's how we're going to analyze the efficiency of our program in terms of for every increment of your data input, how much time is added. So basically, that's algorithmic complexity. But we could also talk about the space, because some uh, data inputs can also affect the space. For example, because you're using memory. For example, if additional increments of your data input, how much space would be needed for you to efficiently execute a certain program? So basically, you can implement algorithmic complexity, or you can measure algorithmic complexity in terms of time and also in terms of space. So basically, it's a way to estimate how the performance of an algorithm grows relative to the input size. I think in the Python programming examples that you had before, so you have some data structures there that contains several elements. So how much processing time would it take if you add more elements? So basically, as you change the input or as you increase the input, how much time would be added? How much time would be added to the execution of your program? So that's basically algorithmic complexity. And I'm showing here actually I have here some types of functions, okay? So in mathematics, we can actually classify function as for increasing functions in this case, except for the constant function. So we have the constant function here, just a horizontal line, and then a linear function. For example, y is equals to x is just a vertical line, and then a logarithmic function, this one between the constant function and the what do you call that? The identity line or the linear function. But as you can see, you can analyze these different functions here: logarithmic, polynomial, and then x log x, and then quadratic is also a polynomial, by the way, and then exponential. It's not very visible here, the uh, how the exponential dominates or the factorial dominates the exponential and the polynomial. But if you are going to move up, if you're going to pan this Desmos scientific calculator, I just use Desmos. It's actually a free graphing calculator online. So I use that. If you move it, if you pan that on the upper portion, you will see that this one will actually dominate this one and this one. A better representation would be if we use an exponential scale on the y-axis, as you see here. So you can see here the scale on the y-axis is by powers of 2. And if you do that, it's clearer how the different growth of these different type of functions actually compare with each other. So you can see here the constant function, the logarithmic function, this one is the linear and log n, this one is quadratic, this one is exponential, and this one is factorial. So what is the relationship of this? So basically, what we're trying to do here is we wanted to come up with some function, an upper bound function that would bound the number of execution steps for a particular algorithm. So each of the algorithms that you are going to, for example, implement, for example, in Python, you can actually basically count the number of steps or the number of instruction steps or execution in that program, and then you will see that there is a relationship between the input or the size of the input and the number of steps it required for you to finish the calculation or the execution of the function. So these are some of and there's actually a notation for that. And that notation is called the big O notation. So I'll just be showing you some of the algorithms I've shown before. And there is and the different big O notation. So basically, if you want, I'm showing here the worst case, average case, and best case scenario. So why are there 3 cases? So basically, if given the same amount of input, okay, sometimes even if you have the same amount of input, sometimes some algorithms will take longer take longer than other algorithms, even given with the same number of input. How is that? It depends, for example, how those inputs are arranged. For example, if you are working with a sorting algorithms and random input is almost sorted in a way. So there are some algorithms that lend itself well to that kind of ordering or that kind of sequence. So it would go probably faster, or it will finish faster than if had it been that the ordering is totally random. Okay, so basically, you can have the best case if it's already somehow almost sorted, and the worst case if it's totally random. And also there's some average case. So that's why there are 3 cases for the big O notation. So this is the big O notation. So these are your algorithm names, and this is a big O notation. It represents actually a level wherein how efficient your algorithms are. For example, bubble sort is O(n) squared, and quick sort is O(n) squared. Merge sort is O(n) log n. Okay, so meaning merge sort is more efficient than quick sort and bubble sort. For example, linear search and binary search. Linear search is O of n, but binary search is log n. So going back to this, we would rather choose those algorithms in the lower part. For example, log n is a better algorithm than n, okay, O of n. But O of n is a better algorithm or more efficient algorithm than O of n log n. So we wanted to veer away from the exponentials and the factorials and the higher ordered polynomial. If you can find a big O notation for a particular algorithm that is lower, for example, if you can find a n or log n or constant, so those are the better algorithms. Okay, so these are some examples of the algorithms and their big O notations. This one for the graphs. So here you can see it depends on the input. You can see here the bar sign with the V and the bar sign with the E. That's actually the number of vertices and the number of edges. Okay. So it really depends on the type of the particular problem or the particular data structure or algorithm you're working on. So it depends on the input. Sometimes if it's a graphical structure, it would be based on the number of edges or the number of vertices. So this one for the quantum algorithm, showing you these are some of the famous quantum algorithms. And as you can see here, the quantum complexity is so much better than the classical complexity. So meaning that if you're going to implement uh, some of the problems, okay, that these algorithms are trying to solve, it would take you some, for example, in the Shor's algorithm, exponential uh, complexity. So we don't want that. So if you can have a better or a lower complexity, that's better. Okay. Now let me try to explain the big O notation to you further. So big O notation, it's a notation. So I've already shown you the notation itself. It's an O with a parenthesis, and then inside the parenthesis, it's usually in terms of an expression. Like for example, based on in terms of the number of inputs of that uh, particular algorithm. So a big O notation is used to measure how running time or space requirements for your program grow as input size grows. So it's a function of the running time or the space requirements, and then in terms of the input size of the data. Okay, so it's a simplified analysis tool for an algorithm's efficiency. So um, you don't actually, I mean, for every program that you write, it's better if you have somehow a conception of the complexity of the algorithms that you are working on. So if sometimes you can find in literature, for example, what is the complexity of a particular algorithm, and then if you're choosing between two, for example, you found out that this algorithm is O of n cubed complexity, and this other algorithm is O of n squared complexity. So which one are you going to implement? So you would rather choose the O of n squared, the algorithms with the O of n squared complexity, because it is more efficient. And then complexity in terms of input given the size n, and then it's also in the big O notation or in the algorithmic complexity, we're not really after or we don't concern ourselves with the specs of the machine. For example, if you're going to use for example, Celeron or an M2 processor, or in terms of the CPU clock, that doesn't really count here. So what we're trying to count here is the number of based on the algorithms itself, not on the machine. So this is machine independent. So what we're trying to do is to count the number of steps or the number of, for example, loops, or the number of cycles that algorithm has already or has traversed, for example. Okay, and then yeah, we're basically after the basic computer steps. Not it doesn't matter whether you're using or what specs of computer you're using. And it's also, yeah, as I mentioned, you can measure the complexity in terms of time or also in terms of space. But usually we do the computation for the time efficiency. I just would like to somehow emphasize that sometimes a particular algorithm will improve the time complexity if you do something about the data set. For example, if you structure that data set in particular data structure, then it will become less, the time complexity will be improved. Sometimes, but the thing is you have to do additional processing for the data so that that data, for example, will be processed more efficiently. So there are some trade-offs with regards to time and data structure. So big O notation describes the performance of an algorithm as the amount of data increases. It is machine independent because we only count the number of steps to completion, and it ignores smaller operations. So basically, it's a big O notation provides an upper bound for the function that represents the uh, the input size and your, for example, the running time of the algorithms. Example here, n, for example, is the amount of data, like the variable x. And these are some examples of the big O notation. O of 1, this is constant time. O of n, this is linear time. O of log n, this is the logarithmic time. And O of n squared, this is quadratic time. So as you can see here, the best is the O of, if you can do a constant time with your algorithm, that's better. But if not, so linear, logarithm is actually better than the linear. And then logarithmic, I mean, linear is better than the quadratic. So types of measurement, worst case, best case, and average case. Actually, in computer science, we use several notations, but the most common one is the big O notation. You'll sometimes encounter big omega or big theta. So those are some versions of big O, but big O is for the upper bound. I think big omega is for the lower bound, and then big theta is the average case. Okay, and you will also encounter like small o, small omega, but we're not going to delve into that because mostly in scientific literature, we only when they describe the complexity of some algorithms, they only talk about big O. They use big O most often. Okay, so general rules, ignore the constant. So if you're, for example, if you have in your function, if you characterize, for example, if you have characterize the running time of your algorithm in terms of a function, running time, for example, 5n, so you're going to ignore the constant. You'll just use O of n. And you can see here the certain terms dominate others. So ignore low order terms. So let me give you an example so that you'll get the hang of it. So I'll have here a table. We have the execution time in terms of input n and the big O notation. For example, you count or you analyze your algorithm and you come up with this function. Okay, there are techniques on how to come up with a general term for that. But it usually starts with a recurrence relation. We call that a recurrence relation in discrete math. But you can generalize that, and you will come up with this generalization of a function. So T of n is the total time of the execution time, and n is the input, or in terms of data. For example, you have this relation, or you have this function, T of n is equals to n squared plus 30n plus 2. So the big O notation for that is just O of n squared. So we'll just take, for example, in this case, this is a polynomial. You'll just take the polynomial with the highest degree and ignore the constant coefficient. So how about this one? So this one is O of n to the 6. Okay? How about this one? 2 to the n to the 4th plus n cubed minus 3n squared plus 4n minus 5. This is O of n to the 4th because that is the degree of this polynomial. And you would ignore the numerical coefficient of 2. So just O of n to the 4th. How about this one? T of n is equals to 100n squared plus 3 raised to the n. Okay, this time, the exponential will dominate. So that term will dominate. So that is going to be an O of 3 to the n. Okay, so remember, exponential is greater than polynomial, polynomial is greater than constant, okay? In polynomial, so you have the cubic, quadratic, and then linear. How about this one? N log n plus 0.5 n squared. Okay. Uh, 5n log n plus 0.05 n squared. So this is O of n squared because the first term is n log n and the second term is, even though it has a coefficient of 0.05, which is relatively small, but in the long run, that n squared will dominate the the n log n. So that's going to be the O of n squared. So remember that the O of n squared represent the upper bound of the function if you're going to represent the number of execution times in terms of the input size. So this is the big O complexity chart. As you can see here, the O of n factorial, O of 2 to the n, O of n squared, O of n log n, and sorry. Uh, Usually we're away, we try to exponential time. That's a no-no actually in computer science. So we want to find an algorithm that would convert that exponential time to polynomial time, or better, linear. Okay, so these are some examples of some algorithms for each of the, for example, constant time, random access of an element in an array. So the Python dictionary is an example of this one. Inserting at the beginning of the linked list, so that's constant time. Logarithmic time, binary search. Okay, this is logarithmic time. For example, if you're trying to find, an example of the binary search is when you want to go to a particular page in a book. Okay, you don't go from 1, 2, 3, 4, 5. So that's linear. But what you do is you open the book in half, and then if you overshoot, you go to the left. Okay, then you open that page again. So basically, that's effectively that's kind of a binary search you're doing there. Okay, so that's logarithmic time because if, for example, if there are 32 pages, if you want to go linear, if you want to go to page 33, you have to go 1, 2, 3, 4, up to 32. But for example, if you want to go to a particular page, you have that. Okay, so the 32 divided by 2, so you just left with 16. So that's one step already. And then divide 16, that's going to be 8. So that's the second step. Divide 8, it's going to be 4. That's a third step. Divide 4, it's going to be 2. And then divide 2. So basically, you just have 5 steps instead of 32 steps for the linear time. Just 5 steps. So that's why it's logarithmic. It's actually logarithm based too. Okay, so these are other examples for each of the big O. Yeah, we have the linear time, looping through elements in an array or searching through a linked list. O of n log n is a quasi-linear time. So examples are quicksort, merge sort, heap sort, and quadratic time, insertion sort, selection sort, and this one, a notoriously hard or very complex problem is this TSP, or the traveling salesman problem. So in classical computing, this is more than exponential time. So it's a very complex problem. So I don't think it's also one of the hardest problem in computer science. So we want to avoid exponentials and factorial time. Okay. Okay. Let me just I'll try to explain how, for example, given a code, how do we count? Okay, for example, given this one line of code, so this is just uh, O of 1, independent of input size, so this is constant. This is just O of 1. So constant time is O of 1, okay? Big O of 1. How about a series of constant? For example, you have three, uh, three lines of code here, okay? Assignment, assignment, and then print, okay? So you have 3 lines of code. So let's see how we compute for the big O of this. So you have O of 1 for the first, O of 1 for the second, O of 1 for the third. So you have 3 O of 1. So 3 times O of 1 is actually still O of 1 because we ignore constant. Okay? So this, even though you have 3 or many different lines of code, which just takes O of 1, steps, so it's still O of 1. So the big O of this is still O of 1. Now, example of linear time. Example, you have a loop, okay, for x in range 0n. So this is a Python code, print x. So print x is O of 1, but this is a loop. You have to do that n times. So it now becomes linear. So this now becomes O of n. Okay? So this now becomes O. So n times O of 1, since print x is just O of 1, but you have to do it n times, so it now becomes O of n. So this is linear. How about this? There's an assignment, so that's O of 1, and then you have a loop, which is O of n. So O of 1 plus O of n is still O of n, because you will get the higher. We're all in the big O notation. We always get the worst case. Okay, the worst case scenario. So in this case, you have O of 1 and O of n. So overall, you have the O of n for this snippet of code. How about this one? This is an example of quadratic time. Usually, if you have a loop within a loop, that's already quadratic. That will tell you that it's quadratic. So this is a loop within a loop. You have for x in range 0n, and then for y in range 0n, and then print x times y. Print x times y is just O of 1, so that's just one step. But you have to do it y times, okay, for y in, and then you have to do it, sorry, n times, sorry. You have to do it n times for that inner loop, and then you have to do it for each of that inner loop. You have to do it n times again for the outer loop. So n times n is n squared. So that's why it's quadratic time. So this is an example of O n squared. And how about what if you have, for example, this one? Let's take this one. So you have here, by the way, I think this is JavaScript because it has semicolon. I remember Bobby mentioned a while ago that in Python you don't use semicolon. So I think this is in JavaScript. X is equal to 5 plus 15 times 20. And then you have a for loop. And then you have, inside the for loop, you have print x, which is just O of 1, just one step. And then for x in range 0 to n, and then for y in range 0 to n. So let's analyze this snippet of code. What is the complexity of this one? So this one is O of 1. This one, this loop here is O of n, right? But this loop here is O of n squared. So overall, we would like to take the worst case already, the worst case. So in this case, O of n. O of n will dominate everything there. So O of n squared plus O of n plus O of 1. So you still have O of n. Okay? So I have already given you several examples. I hope by now you know how to analyze your code in terms of complexity. Okay? So sometimes it's not very intuitive. You really have to broaden your mind to do some thinking or to do some calculation in your mind because there are some things, for example, like sometimes you think it's not very intuitive. Sometimes you think it's just linear, but it's actually exponential. So those are the things that you have to think about. What else? Okay, how about this one? What if your code has if, else, if, and else? Okay. So in this case, since we're always, you have to to choose the worst case. So in this case, for example, in this case, if f x greater than 0, you have here an example, a snippet of code that takes O of 1 or constant time, else if, and then you have here under else if, you have a snippet of code that takes logarithmic time, and then in the last else, you have a snippet of code that takes n squared or quadratic time. So in the overall, you would consider this, or you would tag this as quadratic because that's the worst case in whether in this if else if else statement. Okay, so this is still O n squared if there are n squared number of times within those branch of control structure. Okay, another examples here. I think this one is in C or in JavaScript also. This one on the left is a linear time. So given n, this is just for n equals 1 million, so it's approximately 1 million steps. But on the right, you just have 3 steps. So this is just constant time. It doesn't depend on n. It's simply as computing the value. Okay. What else? This one are examples in Python. So this one is a example of a quadratic. Basically, if you have uh, an inner loop, so you have, for example, in this case, for I in range n, for j in range n, print blah blah blah. So this one will be in quadratic square. Oh, in quadratic time, since you have for a loop within a loop. Okay, so if you want to avoid, if you can actually just have a sequence of loops, so that's better than having an inner loop, or if you have another inner loop, so that will compound itself. So you're going to be worse than if you can find a way to actually get just simplify the number of steps. So this one is example Python quadratic time, a Python script that shows quadratic time. This one is a comparison between linear search and binary search. So linear search will just take linear time, consider, and binary search is better because it will just take logarithm time. So given an array here, so you're just going to search for a particular number. For linear search, you have to go from start to finish. But for binary search, it actually it actually half the or divide the arrays into half and then look for each one. So it's going to uh, divide, and then if it's not there, you have to go to the other array and then half it again until you find the number that you're looking for. Lastly, I just added this because Sir Bobby mentioned when he was when he was talking about Python dictionary. So what is the complexity for Python dictionary? It's actually O of 1. Okay. In Python dictionary, you use actually there's a mechanism called I use a hash table to implement that. But generally, it's if you're going to work with Python dictionary, it's just a constant time. So I think that's all. If you have questions, thank you for listening. I hope you learned something from me. Thank you.
All right. Thank you for that, Sir Elmer, for that very wonderful talk on complexity of algorithms. And yeah, throughout the lectures, now aside from what Sir Elmer have shown, we will see how certain algorithms that we implement on quantum computers might solve some problems faster than classical ones. Of course, there's some other talks about building the quantum computer itself. It's harder to build a quantum computer, but for those certain problems, no, we would have a sort of advantage, right? We would have advantage, and sometimes because we sometimes call that as quantum supremacy, right? Okay, so we discuss this so that you can understand better, right? Like we don't do quantum technologies for nothing. These technologies definitely have something to give, something to improve on our presently used algorithms and technologies. All right. Okay. So we're nearing the end of our lecture for today. So some announcements. The homework will be sent and everything else will be sent. The recording will be sent. We'll do our best to send everything by tonight so that you can work on it as quickly as possible. And also, yeah, we hope that through the extended period of break, you would have some time to really dig into the math and do our homeworks properly. All right. And also, we will announce this again next week, but just a teaser that we will be soon be opening the community, and yeah, we will invite some of you and most of you to be members of the society. So yeah, watch out on an email regarding that, and also an announcement on the next lecture. All right, Sir Bobby, you unmuted po.
Yeah, sorry. I was I was going to say that when we end, I'd like to meet the members of One Quantum to have a post, a review of what of the sessions.
Awesome. All right. Okay. At this juncture, we ask everyone, if you can, to please open your cameras so that we can have a photo up. Right? Stop my share screen. Hello, hello, everyone. There we go. Hi, hi. Hello. Kamusta? Yes, yes. Okay. All right. Hello po. Good evening. Good evening. And we hope that you're comfortable and cozy there. All right. So, yeah, can I ask one from the team to take a screenshot of the pages?
Okay,
Okay,
okay, you did. Sorry, Elmer.
okay, smile. 1, 2, 3, smile. So there are four groups. So that's the first group. I'll take a picture of the next group. Okay, 1, 2, 3, smile. Okay, next group. Uh, Kindly open your camera for those who hasn't opened your video cam. Okay, 1, 2, 3. Okay, last group. Okay, kindly open your cams. 1, 2, 3. Okay, great.
Awesome.
I'm
Thank you
done
po.
taking pictures. Yeah.
Okay. Thank you po for that, sir. At this point, yeah, we will have our attendance form. Okay, so yeah, you can fill up our attendance form on the chat box, and afterwards, and you can leave the call na, and yeah, if you have any questions, you can message Discord. Yeah, we're there, and we'll try to reply as soon as possible. All right.
Thank
Okay.
you.
Yep. Yep. Thank you, guys. See you next week. Yeah.
Right.